Hello guys, Mr. G here, and this time we're going to be doing some challenge questions about momentum and impulse. Remember, you are going to write exams quite soon, and then this is important and was done long ago. Then later we'll do more videos on organic chemistry, but I think it's good to record and go back a little bit. So these questions are quite challenging. They were compiled by Professor Rodriguez, so we're going to be looking at these questions. Okay, question 1 say two trolleys, and this is a selection, it's a multiple choice question. Okay, two trolleys A and B with the same masses are placed on a horizontal frictionless surface with a spring compressed between them. A block with the same mass as that of one trolley is placed on the top of trolley B as shown in the sketch below. When the spring is released, the trolley is moved apart due to the force exerted by the spring on each other. Which one of the following statements regarding the magnitude of the impulse of the force exerted on trolley A and the magnitude of the change in momentum respectively are correct? Magnitude of the impulse exerted on trolley A is, and they give you two options, double the magnitude of the impulse of the force exerted on trolley B. Now, note the following. The magnitude of the force is the same, that is Newton's third law. So F net here for A and B and A is the same, and therefore the impulse is going to be the same. So in this case, if you go on reading, they say that the magnitude of the impulse is equal to the magnitude of the impulse of the force exerted on trolley B. Now that is the only option that matches here, because they say that it's the same. Note that here net force A on B must be equal to force B on A in different directions. All right, they're talking about the magnitude there. Now the impulse is equal to F net divided by change in time. F net is the same and time is the same because there is an interaction. So the only option here is B. That one was quite simple. Now the problem starts with the question 1.2. They say two pad balls move along a frictionless flow as shown in the diagram below. They stick together after collision. If ball A is moving to the left at 15 meters per second and ball B is moving to the right at 25 meters per second, and if the masses are equal, what is the common speed after collision? And now in this case we have to use the conservation of momentum, and let's start doing that even before looking at the possible answers there. Now I am going to start from here. In the mass A multiplied by the initial velocity A plus mass B multiplied by the initial velocity B is equal to mass A multiplied by the final velocity A plus mass B multiplied by the final velocity B. Note the following. They are moving together after the collision. So here we have that the final velocity, which is the same, multiplying the addition of mass A and mass B. Alright, so that is important to notice here. Now, what else we have to know? We have to know that mass A is going to be equal to mass B because there is the same type of balls here. So if you then work with the masses here, and it's really not bad. In this side here, what we have is that mass, I'm going to just write mass is the product of VI A plus VI B equal to, and when you solve here, because it's the same masses, we have 2 mVf. And guys, here the masses simplify each other. These two masses simplify each other because they are the same. So what do we have here? What do we have here? We have that Vf is equal to initial velocity A plus initial velocity B divided by 2. When you substitute here, you will have which is 25 minus 15. Why minus 15? Because it's in the opposite direction. So either of them you have to give the opposite direction there, and everything is divided by 2. When you solve this one, the answer is 5 meters per second. In actual fact, it's to the right, but they only want the magnitude. So the correct answer is going to be 8. This one is a little bit more tricky, guys, and you do have to do calculation. You cannot just guess. This situation of the mass may be tricky or even confusing, but but it's not that bad. Now let's go to 1.3. A trolley A of mass 0.4 kilogram masses and a speed of 3 meters per second has a head-on completely elastic collision with trolley B at 0.6 kilogram mass initially at rest. After the collision, the speed of trolley B is, and they want to calculate after the collision the speed of trolley B here. Alright, now what we have to know here, first of all, that the collision is going to be elastic, and that means that both kinetic energy and momentum are going to be conserved. Obviously, we're going to start with momentum, which is the easiest one. And let's first have a small drawing of what is happening here. Alright, so now here is the drawing of the sketch of what is happening. Initially, trolley A is moving to the right or to the left, they don't say direction, it's not important, and then it's going to hit trolley B, which is at rest. And after the collision, important, they're going to be moving, both of them, but we don't know how are they going to move. So that's why we cannot have velocities there. So before we begin, we're going to start with conservation of momentum to get the final velocity of trolley B, which is the question mark. And I'm going to start with the law of conservation of momentum the same way we started before. Now, I want you to notice that all these numbers are multiples of 0.4. So we can divide everything by 0.4. We can divide everything by 0.4. And we are going to have here that 3 is going to be equal to VFA plus 1.5 VFB. And here we have an equation because we cannot go further on. We have two unknowns. So this one is going to be called equation 1. Now what we're going to do later on, we're going to carry on working with conservation of kinetic energy. Remember, the collision is to be elastic, okay? So we're going to go there. Now to do that, we start saying that the total kinetic energy initial is equal to the total kinetic energy final. And if we carry on, and here we have equation 2. We cannot carry on because we have two unknowns. So now we're going to work with those two equations. So if we arrange here for the final velocity A, we get that is equal to 3 minus 1.5 final velocity B, and all we have to do is to substitute in that equation 2, which we are going to do real fast. And once more, we are dealing here with maths, guys. We're dealing here with maths, but we are going to do that one here. And so the answer is C. This is a tricky, challenging question. It's a good question for an exam, okay? So there's a lot of work. You have to make application of both conservation of momentum and conservation of kinetic energy. But saying no more, let's go to the second question, which is also challenging, guys. This question said, trolley A of mass 3 kilograms at rest on a frictionless table is attached on by a horizontal force of 19.6 Newton. At the same time, block B of mass 3 kg resting on a frictionless horizontal table is connected by a light inextensible string which passes over a light frictionless pulley to another block C of mass 2 kg. Both blocks A and B are the same distance from the edge of the table, which is 1 meter. State Newton's second law in terms of momentum in words. Which trolley A or B reaches the edge of the table first? Explain your answer. And we're going to do those two first, the 2.1 and the 2.2. So let's start by 2.1. And that first one is the net force acting on an object is equal to the rate of change in momentum. If we write the formula, we have that F net is equal to the rate in change of momentum. And let me tell you something, guys. This definition is the one that is going to help you to explain the question 2.2, which trolley A or B reaches the edge of the table. First, explain your answer. Now, this is very tricky question here. If we go to the second trolley, to this one here, this object have two forces acting there, okay, which is going to be this force, which is weight, and have tension. But this tension is equal to this tension here, and is going to be internal forces, let's say, for example, these two forces. So let's take the whole total entire system. The table is frictionless, so there is not friction in none of the two cases. So there is not friction here, and there is not friction here. Now, if you calculate the weight, which is what is most of you going to do first, this weight is equal to mass multiplied by acceleration due to gravity. So we can see that the weight acting on this specific object is going to be equal to 2 multiplied by 9,8. And there is a tiny thing here. The weight of this object is going to be 19,6 Newton. And notice the following. This and this one here is the same. So the net force is going to be the same. So the net force in this case here is going to be the same of the net force in this case here, which is 19,6 Newton. 19,6 Newton. Now people say, okay, but if they have the same force, there is not friction, well, they will reach the end of the table at the same time, but it's not so. Why not so? Because of the total mass of the system. If you go to total mass of the system, in this case we have mass of B plus 2 kilograms. If you substitute, you will have, which is 3 plus 2 is equal to 5 kilograms. But in this trolley here, in the first one, the mass of the trolley is only 3 kilograms. So you are applying the same force but to two objects with different masses. Therefore, the rate of change in velocity, which is the acceleration, will be greater in the first case. And this is coming from Newton's second law. The rate of change in momentum is the same in both cases, guys, because F net is the same and the time is the same. But remember that acceleration is inversely proportional to the mass. So that object that have less mass, which is this case here, will therefore also have a greater acceleration. And if it has a greater acceleration, it will reach the end of the table faster. It is very, very tricky. The rate of change in momentum is the same in both cases, but the mass is not the same. And because the mass is not the same, the rate of change in velocity is different. The velocity changes differently, the acceleration is different, and it's Newton's second law, and therefore block will reach the end of the table first. Guys, that is quite tricky. It is really, really tricky. Now, question 2.3, calculate the impulse of the force on block A for the time it takes to reach the edge of the table. So we're going to work with this side here, with this specific point there. And let's quickly, first of all, write the formula for impulse. So question 2.3, let's going to do it in this page. Question 2.3, and they ask us to calculate the impulse of the force. And impulse, remember, is equal to F net multiplied by time. Or we can say that impulse is equal to the change in momentum. And let me tell you something, either of the two options will give you the same answer, so you can apply both of them. If we substitute here, to go a little bit further, impulse will be equal to mass multiplied by the final velocity minus the initial velocity. This is done before. In this case, we don't have the final velocity, we don't have it. In this case, we don't have the time. So both of them, you will have to calculate something before you can answer the question. I think the best way is to use this one, but you can try the other one and compare the answers. So we have that impulse is equal to mass multiplied by the final velocity minus initial velocity. And they are telling you that the object start moving from rest, so the initial velocity is 0. Now we don't have the final velocity, so we have to get it. We are going to go to equations of motions, and look for a formula that can help us. Now the best formula that can help us for this one here would be the final velocity square equal to initial velocity square plus 2 times acceleration multiplied by the displacement. And I want to point something out. Be careful, because people attempt to confuse this one with a projectile, and this one is not projectile. It's on the horizontal surface, an object moving, and so on there. So this one still going to be 0. The initial velocity is the same, so we have that the final velocity square is equal to 2 multiplied by a multiplied by the displacement of the object. And if we use the square root, we have that the final velocity or speed of this object is equal to square root of 2 multiplied by the acceleration multiplied by the displacement, and we can substitute this one right there, guys. Now if we go there, we have that the impulse is equal to the product of mass by the square root of 2a delta x. And then we have another situation here. We don't know the acceleration, and once more we have to carry it to some other way to get that. Now we're going to go to Newton's law of motion. Newton's law of motion, in which net force is equal to the product of mass and acceleration of the object. The net force is given to us. It is 19,6. We have it. There's not friction. The only force acting is the applied force, and the mass is going to be a 3 multiplied by the acceleration. If you rearrange this one, you will get that the acceleration is 6,53 meters per second square. All right, 6,53 meters per second square. And then when you substitute this acceleration there, so we are going back all the time to substitute. Now we have all the data. The displacement is given to us in the picture, which is the length of the table, and it was 1 meter. So if we substitute here, we have the mass is 3 multiplied by the square root of 2, acceleration is 6,53 multiplied by the displacement, which is 1. And when you do this calculation, you shall get 10,84 Newton second. And then they're asking you to calculate the impulse, and the impulse have a direction, so the direction will be to the right. And we are done with this question. This question is not easy, so I'm not going to tell you it's easy, because it's not. It's a lot of multi-step question. The most difficult one so far, I think, to explain why A reached the end of the table before B, because the applied force is the same, or the net force, and that is quite confusing. Guys, I'm going to stop here. There's 2 more questions I want to do. This one is quite difficult. It is quite different. And then I have another one, which is this one here. I'm going to do it, but not today. I'm going to make another video. I don't want to make the videos too long, because then you get tired and you fall asleep in the video, so it's not right. Let's stop here with these 2 questions, and I will set up a video for the next other 2 questions to complete a total of 50 marks. I think I said 50 marks. Is difficult, so we're going to have 2 videos for this test. Thank you for watching. I hope it helped. Go back to the questions, try to do it again, and then watch the video to mark your answers. Thanks for watching. I hope it helped. I hope you enjoy it. Thumb up, Mr. G. Cheers.